So what is it? Well, we've identified it already. We've seen it, right? The respiratory compensation point occurs at the workload really beyond which we've lost metabolic control. It denotes the end of the heavy exercise domain and the onset and the transition into the severe exercise domain. It represents that point where bicarbonate or the availability of bicarbonate becomes so limited in terms of buffering our hydronides and lactate that we lose that respiratory control. So it is directly connected to maximal lactate steady state because we no longer are able to maintain a balanced lactate concentration. Because remember, fundamentally, if we've got a balance in appearance and disappearance, we would get a steady state in lactate, but that's only really possible because you've either got enough inactive muscle fibers to metabolize, or sorry, to take up the excess lactate, or you can send enough lactate to the Cori cycle, or you've got enough bicarbonate to neutralize the lactate. When any of those start to become limited, which they all start to be anyway as exercise intensity increases, it becomes problematic. The big one here is you've lost that safety mechanism, which is the bicarbonate. So here's our data set. We go back to our data set. Here's gas exchange threshold. Here is what's called respiratory compensation point. The point where fundamentally VE now loses its coupling to VCO2. And as Myers states, RCP marks the onset of hyperventilation during incremental exercise. That is the loss of linearity in a plot between VE and VCO2. And as they've written, you can kind of see they're alluding to it here. Actually, the reason why this hyperventilation occurs has not been sufficiently investigated. This was written in 2004, we're 20 years later, and actually fundamentally it's still not really properly been investigated. We've perhaps got a much stronger understanding of it in terms of what is going on. And I apologise, this is a slightly long paragraph, but it's really important for us to kind of get this clear. This is a paper published in 2019. And I'm going to kind of read this section here and lead us into it. During a progressively increasing workload exercise, ventilation follows three distinctive domains regulated by oxygen uptake, carbon dioxide production, and unbuffered acidosis, respectively. The first domain is from the beginning of active exercise to the anaerobic threshold. Now, this is where terminology gets confusing. The anaerobic threshold here is what we're calling lactate turn point, which is gas exchange threshold. The second is between LT2 and the respiratory compensation point, and the third from the respiratory compensation point to the end of exercise. The second domain, so that is between gas exchange threshold or LT2 and RCP, the so-called isocapnic buffering period is characterized by the start of anaerobic metabolism added to the progressively increasing aerobic one, and by the constant production of I don't like the word lactic acid, but lactate buffered by bicarbonates. Okay. There are several determinants of the amount of VO2 increase during isocapnic buffering period. That is between, remember, gas exchange threshold or LT2 and RCP. So that's the change in VO2 at LT2 to respiratory compensation point. And these are the reasons, these are the determinants. One, the amount and rate of lactate production. So remember that starts to accelerate. Two, the amount of bicarbonates available for hydrogen buffering. Three, the CO2 arterial partial pressure, PaCO2 level as regulated by the chemoreceptors and overall sympathetic tone. And four, resting and exercise ventilation, both amount and pattern. In other words, it's kind of alluding where we showed in the graphs earlier on. Fundamentally, once you get into that zone of isocapnic buffering and bicarbonate becomes limiting, you've now got a much higher rate in terms of lactate, but fundamentally a much higher rate of hydrogen production. The net result of that is they then have no natural place to go. They're now in the circulation because they've been pulled from the cell. They're now in the circulation, and the hydrogen ions has that potential to interfere with a lot of cellular processes. But the one thing that happens is that these are detected by the chemoreceptors. And the net result is because they're detected by the chemoreceptors, you get a triggering of a hyperventilatory response. This isn't a second source of CO2, this is fundamentally the chemoreceptors being acted upon by the excess hydrogen ions. What do we start to see happen at this point is, remember that what we said was happening up to the gas exchange threshold, we said in terms of respiration, it was fundamentally tidal volume that was increasing. But once you get into this zone of isocapnic buffering, you start to get an increase in frequency, and then suddenly, as the zone of isocapnic buffering disappears, VE accelerates enormously because of breathing frequency. You've already hit the inspiratory capacity. That will have been hit at gas exchange threshold. That's the amount of air that you can take in per breath, the tidal volume during exercise. So the only thing that now is driving up respiration is frequency, and the reason it's driving it up is fundamentally the hydrogen ions are interacting with the chemoreceptors. They are creating that environment where the only thing to do is you're trying to get rid of CO2. It's not because there is a second any more CO2, or sorry, rephrase that. There's not some surge of CO2. CO2 is now rising disproportionately as it was before. But it's the hydrogen ions acting on the chemoreceptors that drives up respiration, that triggers this sudden rise in ventilation. And this is what we see here. So here we've got the ventilatory equivalence graph, VE VO2 and VE VCO2. Remember, gas exchange threshold was at 210. At 240, just happens to be at 240, it's not as they're not always at the next workload up. You now lose the coupling between VE and VCO2, and you see it here. It's the VCO2 goes up in a linear-like fashion. The VE is the bit that's driving up this relationship. You suddenly increase ventilatory rate because of these excess hydrogen ions acting and being detected by the chemoreceptors. And so this point here, again, we've got a double confirmation. I plotted VE against VCO2 and I plotted the ventilatory equivalence. I've got a double confirmation, and that fundamentally identifies the respiratory compensation point, which reflects the loss of metabolic control and therefore is the point which demarcates the transition from what we call heavy to severe exercise, which means once I go into the severe domain, I can no longer maintain a steady state. And we can see this really neatly here in a paper published in 2004. This is the Meyer paper. But what you can see here is when they have they've done incremental exercise, and they've basically given them bicarbonate to try and affect the outcome of the test. And what they've shown is that when you actually ingest bicarbonate, so kind of a bicarbonate solution, you can actually increase the zone of isocapnic buffering. So the net result is it really shows how important the bicarbonate availability is to this point during exercise.